In this video, I'm going to go over the natural exponential function, its derivatives and integrations, and review a little bit of pre-calc. Also, I'll extend at the very end exponentials and logarithms to just general bases. So just to remind you, the natural logarithm is defined to be a definite integral from 1 to x of 1 over t dt. This is done in such a way so that by the fundamental theorem of calculus, the derivative of this function is then 1 over x. And we also found in that previous video that we defined e to be the single number, so the natural log of e is 1. I said back then it'd be nice to know what e is, and I thought I'd show you how to go about approximating it. So, notice that suppose I define f of x to be the natural log of x. Then its derivative is 1 over x. And if you evaluate that at 1, you get, of course, 1. So that means then that 1 is the derivative of f at 1, but we know how to find the derivative of a function. It's the limit of a difference in function values over a difference in the corresponding x values, inputs, as the difference in the inputs goes to 0. That involves this particular limit. So this limit then has to equal 1. But we know what the function f is. I'll just evaluate it. That's then the same as saying the limit as x approaches 0 of the natural log of 1 plus x minus the natural log of 1 all over x. But the natural log of 1 is just 0. And I can write the division by x to write it as 1 over x times the natural log of x plus 1. Then by using properties of logarithms, you can bring that 1 over x up to get 1 plus x to the 1 over x power, and take the natural log of that, and then take the limit of this. But continuity means if a function is continuous, you can change the order, swap the order of function evaluation and limits. That means that limit is the same as saying take the natural log of the limit of x plus 1 to the 1 over x as x approaches 0. This means then the natural log of this number is 1. So the number then has got to be e. So then this is a way for us to find out what e is. You literally just evaluate the function 1 plus x to the 1 over x power for powers where, well, for x values where x gets closer to 0. And that's what I did here. I just typed into the function and I evaluated it for where x is getting closer and closer to 0. And you can see that the corresponding function values get closer and closer to e. Now there is a problem here. And the problem is that we actually don't have a formal definition for what we mean for exponents in general. Yeah, you know what it means for x squared, x cubed, but you don't know what x to the pi means. So we need to fix that. That's what we're going to do for the rest of this video, is to fix that particular issue. And we'll address lots of other things along the way. So to do so, though, I need to convince you that the natural log of x has an inverse. To do that, we need one more derivative rule. Now, this derivative rule actually has a lot more portions to it. I'm only including the pieces that we absolutely need right now. This is something you'll see again in Calc 2. So if a function is differentiable on a single open interval and the derivative on that open interval is never 0, then that means instantly that the function has an inverse. And second, that inverse actually has a derivative too. So that's really, really neat because we know that the derivative of the natural log of x is 1 over x. And on the interval for numbers above 0, that particular derivative is never 0. So that means then, by this theorem, that the natural log has an inverse, and that inverse is differentiable. It has a derivative. Now, we knew from pre-calc what the inverse of the natural log of is. It's called the natural exponential function. But what we didn't know is that that thing has a derivative. So let's go ahead and talk about that function. The natural exponential function, called e to the x, is just the inverse of the natural log function. That means then, if you ever write e to the x equals y, it's equivalent to saying the natural log of y is x. Now, there are some consequences then of the theorem I just gave you. This function e to the x then is differentiable. That means that it's also automatically continuous on its domain. Also, since e to the x and the natural log of x are inverses, then the natural log of e to the x has to be x, and e to the natural log of x equals x also. That's just writing down the properties of inverses. Also, because we know the graph of the natural logarithm, we instantly know the graph of the natural exponential function, because they're mirror images in the line y equals x. But we also know the domain and range of the natural logarithm, so we instantly know the domain and range of the natural exponential. And we also know the corresponding limits of the end behaviors of e to the x as x either goes to positive infinity or as x goes to negative infinity. That's literally just swapping the limit notation around what we had for corresponding to what we had for the natural log function. And since the domain of the natural logarithm was only positive numbers, the range of the natural exponential function is only positive numbers. Since the range of the natural logarithm is all real numbers, the domain of the natural exponential function is then all real numbers. Now, I don't really want to go into it, but the normal exponent laws still apply to this function. I'd have to prove all of these. That's something I'll do in an extra video. The reason it's interesting is because the way we've defined the function, one of these here, just to show you what's going on, this here says that a function times a function is that same function, but evaluated at a different number. That's an amazing result. So if that's true, it's something I would definitely want to prove. I can't just assume that the exponent's laws are true because I said e to the x. Here, though, the theorem says that they are. I'm just not going to prove them here. Now, we can then use what you have so far in order to solve equations. So let's just do some quick pre-calc review. So if I wanted to solve the equation e to the 2x minus 1 equals 7, I could then add 1 on both sides to get e to the 2x equals 8. You could then take the natural log of both sides. You would then use the inverse property for the natural log and the natural exponential function. Together, this is 2x equals the natural log of 8. And that means x equals 1/2 the natural log of 8. And if you want to rewrite that, you of course could. All right, there you go. That's the first answer. The second one's a little more fun. Notice that you can write that equation as e to the 2t minus 4 times e to the t minus 5. That reminds me of a quadratic function. So if I use really quickly that u is equal to e to the t, then that means that u squared is really e to the t squared. And by properties of exponents, that's e to the 2t. After substitution, the equation then becomes it's really u squared minus 4u minus 5. Oh, and there's an equal 0 there. Equals 0. That can be then easily factored to be u minus 5 times u plus 1 is 0. So that means that either u is 5 or u is negative 1. Separately, that means that e to the t is 5 or e to the t is negative 1. Now we know, though, that e to the t, the range of that function as t varies is only positive numbers. There's no way to solve that one. Here, though, we can use the inverse property to get that t equals the natural log of 5. And that's the only answer. Good. So now let's go ahead and solve some more. Here, the trick is to notice that you can take this equation and write it as e to the 2x is equal to e to the 3x minus 4. And then there's two ways to handle the problem. You can think of it as take the natural log of both sides, or you can use the one-to-one property, that since the exponential function's derivative is always, well, since the graph of the natural exponential is always increasing. The function is always increasing. The function is 1 to 1. So the only way the outputs could be the same is if the inputs were the same. And then from there, it's easy. Just add 4 on both sides, subtract 2x on both sides, and you get the only possible solution to the problem. Great. Now, the last one. Here to solve a logarithmic equation, I will subtract 3 on both sides to get the natural log of x minus 3 equals 2. And then I'll exponentiate each side. That'd then be e to the natural log of x minus 3 equals e to the second power. By the inverse property, e to the natural log of x minus 3 is just x minus 3. That equals e squared. And by adding 3 on both sides, you get the only possible answer. There we go. Good. Now we've done a little bit of pre-calc review. Let's go and try to figure out what is the derivative of e to the x. Now we know from the derivatives of inverses theorem that this function is differentiable. So the derivative of e to the x does exist. I just don't know what it is. So y then is a differentiable function of x. I'm going to use that fact. I'm going to rewrite this once. I'll write it instead in terms of a logarithm. Now that's the same equation, but it's done now implicitly because y is not solved for. I can then take the derivative in terms of x on both sides. The derivative on the left-hand side, think of it like logarithmic differentiation. You would have 1 over y times the derivative of the y over in terms of x, and that's equal to the derivative of x in terms of x, which is 1. You can then solve for dy dx. To get dy dx is actually just y. But we know what y is. Y is e to the x. Putting this together then, that says that the derivative of e to the x in terms of x is just e to the x. That's great. That's wonderful that we have a function that does that. In fact, it's one of the only functions out there that does that. There's one other function that's like this, the function 0. The derivative of 0 is 0. But there's no other function out there whose derivative is itself, except for multiples of e to the x. So by the chain rule, if we replace x with a function of x, then the derivative of e to the u in terms of x is e to the u times the derivative of u in terms of x by using the chain rule. We can then use this to find derivatives of exponential functions. So why don't we just do that? Let's just practice a few of these. So I want to know what's the derivative of 5 times e to the 4x. So then this would then be equal to, I take the constant and I take the derivative of the rest. But that is the constant. But the derivative of e to the 4x is e to the 4x. You then multiply it by the derivative of the exponent. Notice, don't think of it as bring the exponent down. That's a different rule. That would then be 5 times 4, because the derivative of 4x is just 4. You then get 5 times 4, which is 20 e to the 4x. And I skipped a small step there because, well, frankly, I'm running out of space. This then equals the derivative of e to the sine of x. It's the same rule. So then the derivative of e to something is e to that something. You then multiply it by the derivative of the exponent. And that's the cosine. So now we have to decide where we're going to put functions. So when you have exponentials and trig functions and logarithms, where do you write them? There's not really a rule, but generally we tend to write exponential functions before trig functions. So we write this as e to the sine of x times the sine of x. Change that. Times the derivative of sine, which of course is cosine of x. If you want to reverse these, you can, but then you really need to use parentheses. So you could write it as cosine of x in parentheses times e to the sine of x. That way it's really clear what the cosine applies to at all times. Great. The last one. So the derivative of x squared times e to the 2x. That's a product. See, there's a factor and a factor. So I'm going to need the product rule. It would be the first factor times the derivative of the second factor plus the second factor times the derivative of the first. That would then be x squared. The derivative of e to the 2x is e to the 2x. I then multiply by the derivative of the exponent. That's only 2, so I'll put that 2 up front. Then I have plus e to the 2x, and then times the derivative of x squared, which of course is 2x. Now we don't leave the answer this way. We simplify it. And also, pretty much whenever you have a multiplication of an exponential function in a derivative, you're always going to have that factor appear in every single factor, in every part of the product, in every sum and in the summation. So I'm going to pull out some common factors to make my life easier. Notice there's a common factor of 2. There's a common factor of x. And there's a common factor of e to the 2x. By factoring those out, you get then what's left over, which is just x plus 1. So you can write this then as 2 times x plus 1 times e to the 2x. This makes it much easier to do what we need to do with derivatives, which is usually set them equal to 0. So, good. Let's do a quick application then. So I want to know then, what is a linear approximation of e to the x at 0? Now you remember a linear approximation. So the function's values are about equal to the linearization for x near 0. So the linearization then is f of a, which here is 0, plus f prime of 0 times x minus 0. So I just need to know what the derivative is. So we know the derivative of f is e to the x. So f of 0 is e to the 0, 1, plus f prime of 0, that's again e to the 0, that's 1, times x minus 0. That is 1 plus x. So e to the x is about the same as 1 plus x for x near 0. And that's really not that bad of an approximation. I mean, as long as you use like x as 0.1, 0.2, or negative 0.15, these are numbers near 0, and yeah, it gives you about what e to the x is. Let's try a more interesting problem. This time I want to know at which values will there be a relative extrema for this function. So you know how to find relative extrema. We have to find the critical points first, and then we'll use the first derivative test or second derivative test. I'll use the first derivative test in order to figure out where our extrema are, because I don't want to take multiple derivatives. Once I have the first derivative, that really is all I need to find the extrema anyway. So I need the derivative. Well, that means then I need the derivative of this quotient. So to do so, the derivative of f then equals, it would be the numerator times the derivative, sorry, it's the denominator times the derivative of my numerator minus my numerator times my derivative of my denominator. People say this as low d high minus high d low, which is kind of gibberish, but that's okay. It's a way for people to remember it. And then it's all over the denominator squared. So that then equals. So we have our division bar, our x squared. So let's see. Oh, our x squared squared. So that's x to the 4th. I'll just erase that right there. That's our x to the 4th. Then you'd have x squared. The derivative of e to the 4x is e to the 4x. You then multiply by the derivative of the exponent. The derivative of 4x is 4. I'll just put that 4 right there. Minus e to the 4x. And then the derivative of x squared is 2x. Great. All right, so then notice in the numerator, as you saw before in my previous example, there's a common factor. There's a common factor of a 2, of an x, and of an e to the 4x. If you take that product out of x squared times 4 times e to the 4x, you wind up getting a 2x minus. Then divide 2 times x times e to the 4x into basically the same thing, and you get 1. That's all over x to the 4th. Oh, come back, x to the 4th. There you go. So that means equals, just carrying it up here, equals. That means that the derivative, actually, I won't write that. I'll just continue it nicely. So we'll just start a new line. So that would then mean new equation line. That's the derivative of f of x then equals a factor of x at least cancels. So I have a 2 times a 2x minus a 1 times an e to the 4x. And that's all over x cubed because this was x to the 4th. Great, that's the derivative. So now let's just go ahead and solve that the derivative is 0. 4x. So that means then 2 times 2x minus 1 times e to the 4x equals 4x equals 0. Now the only way that product would be 0 is if 2x minus 1 is 0. Because 2 can't be 0. E to the 4x can never be 0. So that gives us our only critical number, a half. Now I could go and find the second derivative and use the second derivative test. But you saw this one was kind of involved, so I don't really want to do that. Instead, I'll use the first derivative line. So the domain of the function does not include 0, so I'll put that in. And my only critical number here is a half. I'll put the first derivative above, and I'll just test points. So take some number bigger than a half, plug it into the first derivative, you'll get a positive number. Take some number less than 0, you'll get a negative number. Oh wait, nope, you'll get a positive. You'll get a positive number. Positive number. And then plug in something between 0 and a half. So if it's more than 0, x cubed is positive. But if it's less than a half, then 2x minus 1 is negative. So that means negative. Now, I put this problem here on purpose because I wanted to make sure you don't screw up. At x equals 0, there's a discontinuity. There can't be a relative anything there. But right here, at this critical number, there is, though, a point on the graph. The function is decreasing and then increasing. So f of a half is a relative min, and that's by the first derivative test. And that's it. Again, notice by doing this, it's so much easier than doing another derivative. Another derivative would just take a lot more time. So, and that's that particular example. Good. Well, now that you have that, though, since the derivative of e to the x is e to the x, then find the antiderivative of e to the x is also easy. The antiderivative of e to the x is also just e to the x. That means then that the antiderivative of e to u, in terms of u, is just e to the u. We can then use that to go and find the antiderivative of functions that have the exponential function e to something in it. It's just a matter of being clever and using a good substitution. For example, here, what if u equals the tangent of x? Then du would equal secant squared of x dx. By using these substitutions, this then becomes the integration of e to the u du, which is just e to the u plus c. And we know what u is, so that's e to the tangent of x plus c. And that's the answer. The other one, here I would like u equal to 3x. That means that du would then equal to, will equal then to 3 dx. That means then that here, I'm running out of room here. This then equals the integration. So if x is 0, then u is 0. And if x is natural log of 2, then u is 3 times that. So it's 3 times the natural log of 2. I would then have e to the u. And since 3 times dx is du, that means 1/3 du is dx. And that's the new problem. So this then equals 1/3. The antiderivative of e to the u is just e to the u. And we evaluate this from 0 to 3 times the natural log of 2. Now, 3 times the natural log of 2, that's really just the same as saying the natural log of 8, because you can bring the 3 up to get the natural log of 2 cubed, which is natural log of 8. So this then equals 1/3. It's e to the natural log of 8 minus e to the 0. That then is 1/3. By the inverse properties, e to the natural log of 8 is just 8, and e to the 0 is 1. So we get the answer, which is 7/3. That's it. Notice this is not really any more difficult in terms of derivatives and antiderivatives than what you've seen. It's just a matter of being careful with the notation. Let's do another application. So let's go do a rate of change or something involving rates. A metal bar is going to be subjected to an extreme source of heat. The temperature of the bar, capital T, as a function of time, will grow at a rate equal to e to the 2t. So we know the rate of change of the temperature in time is equal to this e to the 2t. Suppose t equals 0 corresponds to when the source of heat is applied. How much do you expect the temperature to increase during the time period between 1 second and 2 seconds after the heat is applied to the bar? Now, this is a great example of where you should use what's called the net change theorem, the net change version of the fundamental theorem of calculus. So if you want to know the actual change in temperature, I want to know not what the temperatures are, because I don't care. I want to know what's the difference in temperatures between these moments in time. So now, the net change theorem, the version of the fundamental theorem of calculus, says that this is equal to the integration from 1 to 2 of the rate of change of that function. But I told you what the rate of change is. That's what e to the 2t is. So I actually just need to find out what that integral is. Notice I don't have to find out what the temperature is as a function of time. I can avoid that entirely by just using the right theorem. So this then equals 1/2 e to the 2t, evaluate from 1 to 2, and that is 1/2 e to the 4 power minus e to the 2nd power. And that's the answer. That's it. That's the actual change in temperature. How much the temperature of the bar would change from 1 second to 2 seconds. Okay. Well, now that I have that, let's go on and talk about general bases. So the definition of a general exponential has to be in terms of the natural exponential and the natural logarithm. So the way we define it is that a to the x from now on, whenever we write that down, anything to any power at all, that always means this object. This is a well-defined object as long as a is positive. So the natural log of a is defined. So as long as the natural log of a is defined, so a has to be positive, that makes sense. Then this would then be a number. X, of course, is given to be a number. This product is a product of two real numbers. And e is defined for any real number. So e to something is defined for every real number. So this is a well-defined object. That means then that you should expect that a to the x has a lot of the same properties as e to the x, because it's basically e to something. So in fact, all the exponent rules are still true. In fact, everything you learned before, it's all still true. The only thing that's different is now I've given you a definition for the object. So for example, I'll convince you. What if you want to know what a to the first power is? Well, by definition, a to the first power means it's e to the x here is 1. So it's 1 times the natural log of a. That's e to the natural log of a. But by the inverse properties, that's just a. So a to the first power is a, which you know, but now you have an actual proof based upon the actual definition. Now, we're not interested in going through all the different properties of a to something, 2 to the x, 3 to the x. All that stuff from before is still all true. Still, whatever you learn from pre-calc, it's all still true. It's just that now you have a definition for objects. So, for example, is 2 to the x differentiable? What would its derivative be? So, in general, let's look at the derivative of a to the x. Well, a to the x, though, is e to the x times the natural log of a. And those functions, this one here, oh, go back. This one here and this guy here, those are differentiable functions. So this is a composition of differentiable functions. So this definitely has a derivative. You just have to go through the derivative rule. So the derivative of e to the u is the e to the u, and then you take the derivative of the exponent. This is x times a number. So the derivative of x times a number is just the number. So then this is the derivative of what we mean by a to the x. But this is, by definition, what we mean by a to the x. So we get this really nice version, that the derivative of a to the x is a to the x times the natural log of a. And if you want to extend that to a chain rule version, the derivative of a to a functional exponent is a to that functional exponent times the natural log of a times the derivative of the exponent. Notice, if you just get rid of this part, this is the derivative of e to the u. It's the exact same rule. It's just now you multiply by this factor. So, let's go do some derivatives just for practicing. The derivative of 5 to the x by the rule I just gave you would be 5 to the x times the natural log of that 5. Then you'd multiply by the derivative of x in terms of x, which is 1. That's the answer. Again, I want to know what's the derivative of 2 to the power of 5x plus 3. Well, by the rule I just gave you, that would then be 2 to the power of 5x plus 3 times the natural log of 2 times the derivative of the exponent. Well, the exponent is 5x plus 3. That derivative in terms of x is 5. So we just have to clean that up to make sure it's obvious where everything goes. So this is the same as writing 2 times 2 to the power of 5x plus 3. Then you would have 5 times the natural log of 2. But if you want, you could bring the 5 up as a power and write this as 2 to the power of 5x plus 3 times the natural log of 2 to the 5th power, which is 32. And that's probably the best looking answer out of all of them. But if you have the derivative of a to the x, you also have the antiderivative, because all you do is you undo the only thing that's extra, which in this case is to find the derivative of a to the u, you multiply by the natural log of a. So to integrate, you have to compensate for that future multiplication. You divide by that factor. So the antiderivative of a to the u is just a to the u over the natural log of a. Let's just practice some problems. So this is pretty easy too. This would then be equal to the antiderivative of 3 to the x is then 3 to the x divided by the natural log of 3 plus c. And that's it. That's the whole answer. Now this other one will be a little bit more involved. Notice that there is a weird function as a power on the 4. So then I'll let u equal to the sine of x. Then du will then equal to the cosine of x dx. Since I have bounds, I'll have x and I'll have u. My x values are 0 and pi. I can find the corresponding u values by just evaluating the sine function at these values. So the sine of 0 is 0. The sine of pi is also 0. So then, based upon these substitutions, this would then become the integration from 0 to 0 of 4 to the u du, which we don't have to find that antiderivative at all because we're integrating from 0 to 0. So the answer is just 0. That's it. That's that answer. All right. Pretty much the last problem. So sometimes, though, you will not have a constant as either an exponent or as the base. So there's no rules for that guy. I mean, there is, but you have to memorize it, and it's not worth your time. It's better to learn how to differentiate this specific class of problems by using logarithmic differentiation. So the way you start that off is that you write down, let y equal to the function. Then take the natural log of both sides. Then rewrite that logarithm on the right-hand side. Using properties of logarithms. Now we take the derivative all the way through in terms of x. So the derivative of the natural log of y in terms of x is 1 over y times the derivative of y in terms of x. Then I need the derivative of the right-hand side, which is the product. So I have the first factor, sine of x, first factor, second factor, times the derivative of the second factor. So the derivative of the natural log of x in terms of x is 1 over x. And I'll put this in parentheses to make it very clear what the sine of x applies to, what the sine applies to. Then I add the natural log of x, and I multiply that by the derivative of the sine of x in terms of x, which is the cosine of x. And once again, I'll put this part here in parentheses so it's really obvious what the logarithm applies to. So dy dx then equals, that's the sine of x over x times, and there's not really a good order for logarithms and trig functions. So I'll write this as the natural log of x just times the cosine of x. So I had to solve for the derivative, so I had to multiply both sides by y. That's the derivative. It just has a y in it, which we could easily fix by just replacing the y with what it's equivalent to, which is here is x to the power of the sine of x. And that's it. I would just leave that alone. I wouldn't even bother simplifying it. That's great. This is really, sadly, the way to go about doing these derivatives. If you want to, there is a rule. You can look it up on the internet. There is a rule that you can learn, but it's not worth your time. It's better just to use logarithmic differentiation because that tool can be used in other cases anyway. This way you just practice it. Okay, now that we have the general exponential function, let's now look at the general logarithm. So the logarithm of base a, denoted as log of base a x, is just the inverse of the function a to the x. This means then that the log base a of a to the x is x, and a raised to the power of the logarithm base a of x is also x. In fact, using that very last statement here, using this one right here, you can pretty much instantly get that the log base a of x is really the division of the natural log of x and the natural log of a. All you have to do is just take the natural log of both sides and then solve for the exponent to get this statement. This is called the change of base theorem, and it's the typical way that we go about evaluating the logarithm base a. The important thing is, though, it says that the logarithm base a of x is really just the natural logarithm. It's just the natural logarithm divided by a constant. So there really isn't lots of other logarithms. There's only one. There's only the natural logarithm. Everything else is just a scale factor of it. So, because of that, you can then pretty much instantly get some very simple derivatives. So the derivative of the log base a of x, by using the change of base theorem, you can write this way first. This is a constant, just take it out. And then the derivative of the natural log of x is, well, just 1 over x. So you get 1 over x times 1 over the natural log of a, and that's the answer. So if you want to find this derivative, it's also really pretty easy. It would then be, using the rule that you just saw, it says, to find the derivative of the logarithm, you take 1 over x, x being what the logarithm is applied to. So that's 5x plus 2. You then multiply the denominator by the natural log of the base, and you multiply by the chain rule the derivative of what the logarithm was applied to. That would then be the derivative in terms of x of 5x plus 2. That is then 5 over 5x plus 2 further divided by the natural log of 3. Notice if you just take out, don't look at this piece here. Notice all I did was I took what this is, I put it in the denominator, I take its derivative, I put it in the numerator. The only difference is that since this is not the natural log, I have to divide by the natural log of that 3. So it's just really the derivative rule for the normal everyday natural logarithm. Great. Now you have that. Let's go practice a little bit with more interesting problems. Because now that you have the derivative of the logarithm and the generalized logarithm, you're going to start seeing them in the integrals. So last time when you saw an antiderivative that had a natural log in it, I said instantly, you see that, just make u be it and just hope it works. If it doesn't, there's other things we have to try. Here, I'll just let u equal to the log base 2 of x. Then the derivative of u, the differential of u, is equal to, it's the x goes in the denominator, its derivative 1 goes in the numerator, and you further divide by the natural log of the base, dx. So that means then that dx is really, times 1 over x, is really the natural log of 2 times du. And I'll put that in parentheses to make it very clear what the natural log is actually applied to. Using these substitutions, this then becomes, I'll rewrite it once, that's really the antiderivative of the log base 2 of x times 1 over x dx. So that is the antiderivative of, that's a u, this part here was u, and 1 over x dx is the natural log of 2 times du. So the constant, the natural log of 2, just comes out, and we have the antiderivative of u du, which is easy. It's the constant, natural log of 2. You then have times 1/2 u squared, and we add the constant. So the answer then is 1/2 natural log of 2, that constant, times u squared, but u is the log base 2 of x, and it's been squared, plus c. And that's the answer. That's about as nice as it gets. That's it. That basically gives you an overview for the logarithm, the generalized exponential, the generalized logarithm, and the natural exponential function. You'll notice that you'll find the natural logarithm and the natural exponential function, ln of x and e to the x, everywhere in science. The other ones, you really don't. You really don't see the functions of different bases because you don't need them ever. You can do everything with the natural logarithm. You can do everything with the natural exponential. So there's no real need to use 2 to the x or 5 to the x or log base 4, log base 10. Those are really there just for convenience, to make it look nicer as you do problems. And also because it might make solving equations a little bit easier. That's it. That's the end of this particular topic.